Thank you. So in general, if it's all right with you all, it's perfectly fine with me if you want to stop me at any point to ask questions. I don't mind at all. So let me know if you have questions along the way. So I guess you already got a good chunk of my background, so thank you for the nice introduction there. I'll just highlight a couple of other pieces. Part of it is just, for myself, the research that I enjoy doing the most is more qualitative research. And for those of you who do qualitative research, you know that you always have to acknowledge what your background is, your biases, because that's going to impact the way that you look at things. So I have a tendency to introduce just a little bit about myself. You already heard the different universities that I've been a part of. Some of the key things I've done, looking at differences between the ways that freshmen versus seniors versus practitioners engage in design thinking. So that work was mostly at the University of Washington. So there I worked with the Center for Engineering, Learning, and Teaching with Dr. Cindy Atman. So I'm not sure if any of you have seen her work, but she's done quite a lot of work looking at differences between the ways that freshmen and seniors and practitioners approach problems, the strategies they use, and the way how broadly they understand the problem, different things like that. For my dissertation and for my postdoc, I looked more at the mathematical thinking side of things. So for a lot of students, to be able to go into engineering, you need to take a lot of math classes. You need to be a certain level of goodness. You have to be good at math to be able to be an engineer. But then a number of people I know that have gone out to work as an engineer in industry will tell me stories about how they never actually use the math. They just get the computer to do it all for them. So there's kind of a disconnect there where I think you know, the people who do think that they don't use math in industry, they're not quite aware of the ways that they do use math. So even if they aren't using all the formal differential equations, derivatives, et cetera, that they learned in the university, they still do use math extensively. So some of my research was just trying to characterize all those different ways that mathematics and mathematical thinking are used in engineering. Even if sometimes after we've been thinking in that style for so long, it becomes second nature and we're no longer aware that we're using the mathematics or the mathematical thinking. It's still a part of engineering practice. It's still a part of engineering design. My current interest, though, is more looking at the first year experience where at Purdue, and I'm pretty sure it's true here too, that students, to be able to become engineering students, you have to have taken certain math classes. Your math, part of your SAT score has to be a certain level to be able to be accepted into engineering. But then you come to Purdue, you come to Northwestern. One of the first classes that you take is this very design-intensive class. So you became very, very good at solving these problems where there's one right answer, and it should take you 15 minutes to get that right answer, and most likely it's related to whatever chapter in the book you're in right now. You were very good at that. That's how you get to be an engineer. And then now all of a sudden we're tossing this completely different way of thinking at you where there's many good answers, and you're going to have to spend 6 or 8 or 10 weeks working on this problem, and it's not going to map perfectly to the textbook. With mathematical thinking, it tends to be a little bit more convergent, where you're trying to narrow down a solution. Design thinking, we push you to be more divergent and consider lots of different options. So right now, I'm really interested in how do students go through that transition and learn to balance those two different ways of thinking. And then I'm also really interested in how children begin to learn engineering thinking, where it's that blend of more mathematical thinking and design thinking. How can kids learn that? So sometimes people think, how could you possibly teach engineering to elementary school students? Well, if you think about a basic design process, you can still teach children that they should ask questions to understand the problem better. They should brainstorm multiple ideas. They should compare their options. They should come up with a plan. They should test out their ideas. So there's things that even elementary school kids can do. Sometimes, more and more so, it's becoming actually part of the curriculum that happens in the classroom. But outside of the classroom, there's also a lot of opportunities for kids to be able to begin to develop some of those skills. So some of my research is looking at parent-child interactions. How do parents help their children develop those skills? What do children learn through watching television shows or through museum exhibits? So those are some of my research areas. But for the talk, I'll be focusing more on some of the the teaching and the educational applications. But first, just a little tiny bit about some of the research I did in the past. Again, this was with Cindy Atman. We had asked freshmen, seniors, and practitioners to design playgrounds for us. So those 3 different groups of people, we had them individually come in, and we asked them to think aloud while they were designing a playground for a fictitious neighborhood. And it usually took them about 3 hours to design that playground. So we would push at them, okay, just keep talking, say out loud everything that you're thinking, even if it seems silly, because we're trying to capture what are the different strategies you're using, how you spend your time while you're working on this task. So with the verbal protocol analysis methodology, that's the goal, is to get people to voice their thoughts so that you can then transcribe everything they've said, break it into idea units, and look to see, in this particular instance, what are they doing. And so we looked at what they were doing in terms of different design activities. And the model of design that we use, since there's many different models of engineering design, but this is the particular one that we used. That one came from looking at 8 different textbooks that were used with first-year engineering students to try to synthesize kind of the common model across different textbooks freshmen might see. So in general, the practitioners spent more time on the task than the students did, and in each of the different areas, where definitely the problem scoping is the biggest place, where the practitioners spent a lot more time just trying to understand the problem before moving on to trying to come up with solutions and test the feasibility of solutions. So the experts definitely spent a lot more time gathering information and defining the problem, but they also spent a little bit more time developing solutions, a little more time project realization, where they were making explicit decisions or thinking about how to communicate their solutions. The other thing that we did with that data is we created these timelines for each individual participant. So for each person, if you looked at everything that they verbalized over the course of 3 hours, you could create these pictures. For each of the little blocks, this is the amount of time at the beginning that this expert spent defining the problem. So this person defined the problem, gathered a little information, did something that was not related to the task, gathered more information, defined the problem, that sort of thing. So you can see with the expert, a lot more time gathering information. Definitely a good chunk of time modeling. So modeling here is thinking through the details of the solution. Whereas the senior, really, their process was dominated by modeling. That was the main thing they did. Yes?
Well, in terms of that gathering data, what did that look like?
Yeah, good question. So I left out that detail. So when we were administering the task, we would give people a problem statement. It was about a page long that said, you need to design this playground for this city. Somebody's recently donated a lot so the city can have a playground. You're a local engineer. Some of the things you should think about is designing activities so that at least 12 children can play. It's safe, it's relatively inexpensive, it can be built within 3 months. Those kind of criteria, constraints. Later in the problem statement, it said that the administrator has more information. So if you would like more information at any point in time, you can ask the task administrator for that piece of information. So I collected the data for the practitioners. So I sat in the same room with them, and I had this box of information. So if they asked me, can you tell me what the price of chain for a swing, what's the price of chain at the local hardware store? I would give them that piece of paper that had the price list for rope and chain. Can you tell me whether anybody's done a survey to see what the kids in the neighborhood want for playground equipment? Yes, here's that piece of paper. Obviously, we didn't have all the information they thought of, so sometimes I would tell them, we don't have that piece of information. You can make an assumption. You can, whatever you think makes the most sense. So the information gathering that you see here would include both the actual pieces of information that they asked for, but then also assumptions that they made, because sometimes we didn't have the information they wanted. So in general, the practitioners would do a lot of moving in between different design activities rather than having long chunks of time where they're doing the same design activity. So they would start to think through details of the solution, but then realized they need a little more information, or realized they needed to go back and make sure they understood the problem, or realized that they needed to communicate the solution, rather than just sitting down and focusing on working out all the details for the solution. So. Okay. So in general, from that research and a couple other studies, came to the kind of this set of ideas for our challenge as educators, for things that we can focus on for what we should be teaching students. So definitely the problem scoping activities, that was a big thing, since the experts really did spend a lot more time trying to understand the problem than the students did. So that's one thing that we take away, that I take away now that I'm teaching first-year engineering students. This is a key thing I want to focus on, is helping students to realize how important it is to spend time understanding the problem, to not just take the statement as it's written, but to push at what is the problem really getting at? Are there ways I can redefine the problem to make it more interesting to me? Making explicit design decisions is another thing that the experts did more than the students. In our class, we've tweaked it a little bit to making evidence-based design decisions. That's one of our big focus areas.
Is that what you mean
yes.
by explicit design decisions? If they're evidence-based, or what does that mean?
Yeah, so those are two different things. So the first is just making explicit design decisions of actually sitting down and comparing two options and saying, okay, this one is better for these reasons, rather than just running with the first idea that comes to your mind. You're actually deciding between choices. For our class, we've taken it a step further and added this evidence-based piece to it. So for our class, we tend to emphasize evidence coming from many different forms. So it could be evidence you're citing external sources, evidence you've collected data, evidence you've gone and talked to stakeholders, lots of different forms of evidence, but you're using some evidence to make your decision. Evaluating designs is another thing that the experts were much better at than the students. Communicating design decisions and doing so professionally. And then that design is an iterative process. So you're moving in between design activities instead of focusing on just modeling for a long time. So those are kind of the implications from some of that research that guide how we teach our class. One of the other things that we ask the practitioners, the experts to do, after they design their playground, we ask them to draw a picture. How do you see the engineering design process? So this is my picture, which changes from time to time, but this is my picture right now at least, of how I would describe the engineering design process. So first you need to spend some time understanding the context, what's the culture of the place you're designing for, what are some of the history, who are the people involved. Think about the scope of the problem. How big are you going to make the problem? How small? What are the boundaries? What resources are available? What are the opportunities? Which would include looking at what are other people doing. So in the context of designing first-year engineering classes, maybe it's going and visiting other universities, what are other people doing as your prior art or learning from others. Coming up with ideas, gathering feedback from stakeholders, trying something out, and then sharing new knowledge with others. So I'm going to use this design process to try and describe the things that we've been doing at Purdue with our first-year engineering program. So the first part I'll talk about is just the context of our design challenge of trying to design the first-year engineering program. So the context. So I work in the Neil Armstrong Hall of Engineering. So there's our statue of Neil out front when he was a student. And I work in the School of Engineering Education. So the history of our place. So Purdue had the first Department of Freshman Engineering. It started in 1953. So in 1953, Purdue established their first Department of Freshman Engineering. And then in 1969, Purdue established the Interdisciplinary Engineering Program. I think it's also one of the first of the kind. Purdue had the first Women in Engineering program. The National Society of Black Engineers was formed at Purdue in the 71-75 era. Purdue co-founded the Women in Engineering Programs and Advocates Network. EPICS was started at Purdue. EPICS previously stood for Engineering Projects in Community Service, but now EPICS is trying to move away from that just to make sure that people know it's not just engineering. Students from all majors can participate in the program. So with EPICS, students work on projects for a semester or for a couple years for course credit. So similar to Design for America in some ways, except it's an actual class that you take, but you're doing community service while you're working on design projects. Purdue had the first Department of Engineering Education. It started just in 2004, and then in 2008, it became the School of Engineering Education. I think most places wouldn't necessarily appreciate that department school distinction. A lot of times I still just call it a department. But for Purdue, what that means is that we have a full program. We don't have just an undergraduate program or just a graduate program. We have the full program. So that's what the school distinction is at Purdue. So again, we began with the freshman engineering program in '53, interdisciplinary engineering in 1969. Around 1953 is when people started to really do research and scholarship on engineering education. And then in April of 2004, those three different things were pulled together to create the School of Engineering Education. So within our department or our school, we have the first year engineering program, we have the interdisciplinary engineering program, so that's our sophomores through seniors, and then we have a graduate program in engineering education. So graduate students who are working towards a PhD in engineering education. So there are three different things going on in our program. And so we're considered a department or a school kind of in the same way that your more traditional engineering departments are. And then our school, we have the first year engineering program. We have professional advisors that meet with the first year engineering students. We have a PhD program, a master's program, research labs. Inspire is our research institute for looking at pre-college engineering education. We, in the future, are hoping to have a bachelor's degree in engineering education. Currently have a bachelor's degree in multidisciplinary engineering and then also a bachelor's in interdisciplinary engineering studies. We have 21 faculty, staff, postdocs. The first year engineering students, some people count at 2,000, some count it as high as 2,500. About 80 multidisciplinary engineering students, again, those are the sophomores through seniors, and then about 60 PhD students. And so here's our faculty. The key takeaway here is that faculty with many different backgrounds. So some of us have degrees, many of us have degrees in engineering, but a lot of people have degrees outside of engineering. So Ruth Strevler, her degrees are biology, zoology, and educational psychology, just as an example. And then again, we have the first year program at Purdue. After students are in the first year program, then they move into a different program. So they would move from first year into mechanical or civil or electrical, or they could stay within our department and move into either multidisciplinary or interdisciplinary. For us, one of the big challenges just in the past few years, our number of first year students did increase dramatically. So we're somewhere around 2,000 now, but just a few years ago, we were below 1,500. So just in the past few years, it's been a big change for us. Other key things to note, we are about 26–27% women, which is still not great because it would be great to be closer to 50%, but generally the national average is closer to 18%. So compared to 18%, we're pretty excited about 26%, 24% international. So this is a big teaching concern, so a big constraint for us to work with as we're designing our activities. When I started in 2007, we taught students in sections of 450 students in big lecture halls, and then they would meet in lab sections of 40 students. In 2008, we switched to classes where students are mostly working in teams of 4. The class size is 120. So for some people, 120 sounds like a lot of students, But having experience teaching in a class of 450, 120 is really nice and intimate. So it's just a matter of perspective. So 120, definitely still a big class, but it's a little bit easier to interact with students. So we have different spaces where we're trying to promote opportunities for students to engage in active and collaborative learning. So this here is one of the classroom spaces. We have all the walls are whiteboards, so you can project on them. Students can draw on the walls. And then we also have a slightly more traditional room space. The key thing with this room is that on each level there's 2 rows of students, so that the students sitting in the front row can turn and talk to the students behind them. So just like you'd be able to in this room. So in the last 2 rows, you all would be able to turn around and talk to people behind you. The middle 3 would be a little bit more awkward to talk across 3 rows. But we were trying to design the room so that if you have a team of 4 students, you have 2 students sitting in the front and 2 students sitting right behind them, so they can still collaborate as a team. I'm gonna skip ahead to get to some of the more juicy parts. Again, making evidence-based engineering decisions in diverse teams. This is our main central focus for the class. So evidence-based decisions, but also learning about diversity and teamwork, and emphasizing design as well as modeling, learning about engineering as a career. So what are your different options? What do engineers do? What different majors can you choose from? And then learning about professional habits, which would include teamwork skills, but also professional habits just of getting your homework turned in on time. We have kind of this big slew of topics, so a continual challenge is to try to narrow it down. Do we really need to do all of these things? But again, I think one of the main things for this past year is to just narrow that list down to the one tagline of making evidence-based engineering decisions in diverse teams, so that the students don't feel like we're doing 50 different things. Instead, we're doing the one thing of making evidence-based decisions. All right. Some of the other practices that we've been doing in the past few years, we're continually trying to make a learner-centered classroom. And so one thing that we do at the beginning of the semester, we ask students to fill out some cards to give us some information, so that even though there's 120 of them, we can start to get to know them a little bit. And so we ask them about their hometown, their hobbies, but then also what are your personal strengths and things you enjoy? How much Excel do you already know? How much MATLAB do you already know? So that gives us some information about where they are. But it's also a way for us to communicate back to them, okay, this is how you filled out the survey. There's actually quite a few of you. There's 18 of you that have never seen Excel before. So if you haven't seen Excel before, that's okay. There's 17 other people in this classroom that also haven't seen it before. You're not alone. And then an opportunity to talk with them, too, about how do you create different charts and graphs using their own data. And then we like to ask them about their strengths as well as things they enjoy, just to talk about the diversity within the room. There's 120 different people that have different interests, different strengths. We're not all in the same category of everybody likes natural science best. Instead, you'll find that some of your teammates, there's some people that like the human sciences best or craft work best. So again, starting with their own information, their own data, to tell them about the diversity in the room, and to teach them about creating charts and graphs. We also explore what is engineering, what do engineers do. We do a lot of activities where we ask them for some quick responses. So in this case, we asked them to look at this picture, write down 10 words about engineering that come to mind. We collect those papers, and then the next class will show them a word cloud to say, these are all the different words that you thought about. Do you all know what this is a picture of? Anybody? This is the Experience Music project. You knew that. So you were going to take a guess. So this is the Experience Music project in Seattle. You can see the Space Needle base right up there. So oftentimes after we show them this picture, then we'll talk about all the different types of people that were involved in creating the Experience Music project, all the different types of engineers as well as other people, to reinforce that as you work on engineering projects, you're working with people from many different backgrounds. All right, so now the flip the lecture part. This is our newest thing that we've been trying. So over the course of the 5 years that I've been at Purdue, every semester we're trying new ideas, constantly trying to improve the class. When I started at Purdue 5 years ago, we did about this much design and more this much MATLAB and Excel types of things. And so that's been one thing that's changed a lot in the past 5 years, is it's more of a this much of the MATLAB Excel stuff and that much of the design stuff. So design in general has been growing. But for this semester, the big change is this flip the lecture model. So this semester, we've shifted from having lecture in the classroom to having lecture be outside of the classroom. So you use your time that you're together in the classroom for the instructional team to be able to interact with the students, as well as for students to be able to interact with other students. So that's one of the key points of the flip the lecture model. So some people video record the lectures. We create them using Adobe Captivate. They're assigned as homework. One of the nice things about it is that students can watch and rewatch the videos. So if you remember a couple minutes ago, I pointed out one of the key pieces of our context is we do have a lot of international students. Generally between 20 and 30% of our students are international students. Obviously, some international students have absolutely no problems with English as a language. However, some of the international students are still new, are still growing in their comfort with listening to English. So being able to rewatch the videos is particularly nice for them to be able to hear it again and again. Likewise, even students who are native English speakers, sometimes the terms we use are new to them. Just the design language that we use, there's some new terms. So they can benefit from rewatching the videos too. And then in class, students are able to work through activities and exercises where there's lots of opportunities for help. When I teach my class of 120 students, there's myself, there's a graduate teaching assistant, and then 4 peer teachers, so 4 undergraduate teaching assistants. So there's 6 different people. In addition to, if you're a first-year engineering student, you would have your 3 teammates as additional resources, people you can talk to. So if you're in a room with all those people that can answer your questions, might as well take advantage of that opportunity. We also have optional videos for students who need additional instruction. So we have some required videos that students have to watch, but then we also give them links to additional videos if they don't have kind of the prerequisite understanding of something, they might need to watch those, or maybe they're just interested in learning more about the topic. So a combination of required and optional videos. So generally what it looks like is outside of class, students are watching the modules and doing some textbook reading and doing some homework assignments. And then inside of class, they will take a short quiz. We want it to take only about 5 minutes, but usually with the logistics, it ends up taking about 10 minutes just for all of the get your paper out, get your pens out, answer the questions. Now we need to collect the papers. It takes about 10 minutes to do that. We go through the class goals and overview, have a short mini lecture, which is generally kind of recapping the answers to the quiz as well as maybe introducing one new idea, but keeping it pretty short. Then spending a good chunk of time on an in-class activity to practice whatever that skill or idea was that they watched in the video. And then some reflection or debrief of that. So this would be our Thursday schedule. Our Tuesday schedule, we have 2 different schools come in and give presentations for the first bit. So, so one week maybe it's civil engineering will come and give a 20-minute presentation, and then construction engineering and management will come and give a 20-minute presentation. The next week maybe we're hearing from mechanical and materials engineering. And then the next part of class is another mini lecture, another in-class activity, another reflection debrief. This at least is how we originally envisioned it happening. But of course, things don't ever happen exactly as you plan. A lot of times it ends up looking more like you have a mini lecture and then a longer in-class activity and a single reflection debrief. One of the biggest challenges is sometimes we don't have time at the end for the reflection debrief activity. That's one place where we need to work on. The challenge is that sometimes students will finish the in-class activity 10 minutes earlier than the rest of the class. So do you let them leave a few minutes early, or do you have them work on something else? Managing that and still getting the reflection activities in is a challenge. So the quizzes, again, they review the content from the previous class. Sometimes, in the past, responses were not graded. That's actually something we did change this semester. The responses sometimes are graded, sometimes they're not. Some instructors choose to grade, give credit based on answering the question correctly or incorrectly. Other instructors actually check for correctness of the answer. Again, we have 14 sections in the class. And so another one of our design constraints is allowing each instructor to have some flexibility to teach in the way that makes sense to them, while at the same time having the experience be somewhat similar for all 1,600 students. Yes?
So you don't have any online quizzes with the videos?
We have, there are a couple of sections that have started using online quizzes. I think they're doing their online quizzes in class right now, but that is one of our next steps, is to look at, can we have the students take the quizzes online before class so it's not taking up class time.
So
yeah.
For the ones that don't have the online quizzes,
yep.
Are you doing any monitoring of whether they actually watch the video, or is the quiz the monitor?
The quiz is the monitor for watching the video. Yeah, yeah. So the quizzes have that quality to them where it's the monitor for did you watch the video. There's also the idea that students can practice with questions similar to exam questions. So another reason for giving them the quizzes is that they start to anticipate what those exam questions could look like to try to reduce their anxiety about the exam. And then it helps them to reflect on what they know or don't know, what are places where they need to do more work. But definitely all those things could be done either paper and pencil or online, in class or out of class. Our biggest concern with the out of class online quizzes is making sure that the student themselves is really the one taking the quiz. So. So one of the quizzes that I gave my students at one point in the semester was to ask them to think about what's the best approach for studying. There was a group of people in a psychology department, actually at Purdue, that did a study where they asked students to predict what's going to be the best method for studying for an exam. Is it just rereading the material? Is it reading and rereading the material? Is it creating a concept map of the material? Or is it practicing retrieving the information? Or in lay language, is it quizzing yourself? So this is people's predictions for what was the most effective method for studying for an exam. So when we show this to the first year students, on the one hand, it's an opportunity for them to think about what they think is the best approach for studying, since they're still developing their study skills oftentimes. But it's also an opportunity for them to practice just interpreting the graph to make sense of the data that's presented there. So this is predictions. So maybe my quiz might be, what do you think is the most effective strategy for studying an exam? And based on the graph, what did the most people say was the most effective method? What actually happened when the psychologists gave people new material to study and then they tested people on that material, they found that the self-quizzing was the most effective strategy. So if any of you have any exams anytime, quizzing yourself will be the most effective strategy as you study for that exam. Yeah?
So would that be like if you're doing a standard engineering course, would that be doing problems in the back of the book, or what does that?
Yeah, so it could be that you're working additional problems in the back of the book. One of the things that we do with our class, at the start of every class, we show these are the learning objectives. These are our goals for the class session. So then we'll tell students that you should go back and look at all those learning objectives and write your own questions. How could you test yourself if you know that content? So writing your own questions based on the course topics, and then seeing if you could answer them. We'd also suggest that maybe you write some questions and your friend writes some questions, and you swap questions. Are you able to answer the questions that your peers created? We do also, before our exams, we share with them copies of previous semester's exams. So we just had our exam 2 last night, and so we shared with the students the exam 2 that we used last semester as well as a year ago, so that they could, again, just practice answering those questions to see what they know and don't know. In-class activities. So this is really the meat of what we're doing during class time now is in-class activities. And so there's a variety of different activities we do. One of the first ones that we have them do is to, in pairs, write step-by-step instructions for making a jelly sandwich. Be as specific as possible. Your procedure may be read aloud. When you're done, please show it to one of the instructional team members. So this was done first day of class. And it had a few different purposes. One was just thinking about how to clearly communicate things. The following week in class, we had them thinking more about writing out step-by-step procedures for doing other things, so it was practice for that. But then we also do read aloud the procedures they come up with for creating jelly sandwiches. So maybe somebody's written out steps of, first you need to take the bread and put it on the plate, then you need to put the jelly on the bread, then put another piece of bread on top. Enjoy. So if I have somebody read that aloud and I'm trying to follow that procedure, I might take the whole loaf of bread, and so I will actually act this out in class. I'll take the whole loaf of bread and put it on the plate, because they didn't tell me that I'm supposed to take the bread out. They didn't say take a single piece of bread out, just put the bread on the plate. And then put the jelly on the bread. You just put the whole jar on the bread. So if you can picture that, you can see how this is actually a good icebreaker for us, just to have a little bit of fun the first day of me trying to kind of push the limits and take it as literally as possible, just to be a little bit silly to break the ice on the first day of class. Other things that we do with our in-class activities, we've done some disassembly of devices, so disposable cameras and expensive calculators. Sometimes our objective is more to have students just think about how it works or how many different pieces are involved. Sometimes it's practice with drawing sketches of the parts and labeling things and trying to think about how it works. We've also used that type of activity for thinking about sustainability and just the more different types of materials that are involved with a product, the less sustainable it is. Sometimes the students also will, or actually I think all the time, they reassemble the devices too. So this is Professor Dimitra Evangelos. She was one of the people who started that initiative in our class. We have them do some building activities. One of them is building the longest bridge out of the connects pieces. We like to do that type of thing the day after they've taken their exam, kind of to give them a little bit of fun after they've taken the exam. But we want to make sure they're not just building stuff and having fun. They're thinking about how they work together as a team while they're working on the activity. With this the bridge activity, we also ask them to plan ahead of time what kind of process they're going to use, those kinds of things. And then they do different kinds of prototyping for their design projects. So you can see that this one was a kind of functional drinking fountain idea where they're using this pump to pump the water through the system. Another challenge that we give them is to use paper waste to make a functional, marketable table to be assembled by a co-op. And so we give them newspaper and cardboard and ask them to create paper tables that can hold up laptops. With that activity, we ask them to do the activity, and then we ask them, so what were all the different things that you did while you were building your table? And they say, oh, well, we had to work together, we brainstormed different ideas, we asked them questions. Another key thing with this activity is we don't tell them up front how much time they have, what materials they have. We just tell them that you have to make this table, and then we push them to think of what are the questions they need to ask. again, to get back to that idea of practicing the problem scoping skills, of thinking about, well, what is the problem really? What are the constraints? What are the criteria? What are the materials available? To do some of that work of identifying the problem and gathering information. When we debrief the activity, we try and take all of the different actions they did in the activity and map that to the design process. So this is usually the activity we do when we're first kicking off the design process, to say the things that you already did, those are all different parts of the design process. And then the reflection activities are usually pretty brief, just what are you taking away from today's class? What questions do you have? Just to prompt them to reflect on what they learned in class today. Okay, so those are some of the things we've been trying. But definitely another key part of the design process is getting feedback from your stakeholders. So midway through the semester, as again, this semester was the first semester we were trying this flipped classroom idea. Midway through the semester, no, I'm sorry, I'm getting ahead of myself. Early in the semester, during the first week of the semester, we asked students for their early feedback on this idea of the flipped classroom. So we wanted to gauge from them right from the beginning what they thought about this idea of the flipped classroom. So for their homework assignment, we actually asked them to do some research, to go find some external sources, to learn about the flipped classroom model, to think about what the benefits were, and to think about whether they have any concerns with the model. So rather than us just telling them we're doing this flipped classroom model, we pushed them to go out and do some research to learn about it themselves. And so this is one of the students' responses. You can see that they went and they found a source, and they actually did a good job of citing the source, which makes me very happy. They say a flipped classroom is a class where students learn lessons at home and later do their homework in class. Since Engineering 131 practices this instructing method, that means the student is responsible for learning the content on his or her own. Then later on in class, the student completes assignments and homework, which contrasts greatly with the traditional method of instruction. This class will be different because I will need to instruct myself on the information that is to be covered. So each student gave us this type of response. So this allowed us to get a sense of what are students expecting to happen this semester, whether their expectations for what this flipped classroom model, this experience might be. So that was some early information. With that, we moved into creating the video modules. How we actually created those, we had faculty develop scripts for different topics and PowerPoint slides. And then the slides were narrated with a computer voice. So that was another design consideration. Do we have a real person voice over the slides? Do we film somebody giving a talk, or do we use the computer voice? And so we went with the computer voice, thinking it would be more consistent across all the different modules, and it would also potentially wouldn't need to be updated quite as frequently. If you just needed to change one piece of the video module, you would still have the same computer voice available to do that little change. Whereas if you had a person narrating it and that person moved on to another university, if you wanted to make a change to the module, you'd have to redo the whole thing. However, there certainly have been some pushback from students about the computer voice. They're not entirely thrilled with the computer voice. So that is one lesson learned. We have tried to keep the modules to be only 12 to 15 minutes long. So in some homework assignments, they might be watching multiple modules, but each one is contained within about 12 to 15 minutes. So it's easy to just get a chunk of it, so that you as a student can sit down for just 15 minutes and watch one module, and then maybe come back later to watch another one. The main topics we've done so far have been more of the MATLAB, Excel, statistics, mathematical modeling. That's been the heart of it. With some of the MATLAB and Excel, we've been able to pull in material that Microsoft has created or MathWorks has created, in addition to our own modules we've created. We've also done some for sustainability, diversity, and teaming. I have Eric Holloway's picture up here because he's really done the bulk of the work. So he really deserves most of the credit in getting this actually up and running. He's our director of instructional labs. All right, so after having students experience that for several weeks, we got some mid-semester feedback from them. So again, if we think back about gathering feedback from stakeholders, now that we've experienced this for a while, we got some feedback from them. So every semester, around the middle of the semester, I give my students a very simple survey. Overall, what's working well with the class. Overall, what is not working well, what could be improved. And most of the time, the biggest thing they talk about is there's too much homework for the class. They have a variety of other complaints. Usually around the middle of the semester, they just are particularly grumpy, and they take advantage of the opportunity to voice their concerns. So here are some of their concerns. So again, I didn't ask them about the flipped classroom model or the concept. I just asked them what's not working well, what could be improved. A few of them thought that we weren't implementing the flipped classroom model to its full potential. So I thought this was very interesting that they were really critically thinking about the flipped classroom model. We pushed them to do the research about it during the first week of the semester. They did the research, they really thought about it, and now here they are, week 8, actually evaluating how well did we do at implementing the flipped classroom model. Most of the students didn't comment on it, but a few of them did. So some of them thought it's not working because there's not enough formal instruction. So this type of response, there's a few of this type of response where generally they don't want to do the flipped classroom model. They think that for me as a professor, I should be standing up in front of the class lecturing at least 50 minutes a week. So there's some of that pushback. Some of them thought that it wasn't working, let's see, because we had them watch the modules outside of class, but then in the classroom there was still some lectures. So again, I said we do have some short lectures at the beginning of some of the classes. So some of them push back on that you should just put all of the lecture content out of class. You shouldn't have any in class if you're going to follow that model. And then the third type of response that I saw, again, this is very interesting. According to the sources we checked at the beginning of the year, a flipped classroom is one where students do the lectures at home and then the homework is in class. This is not how it works in Engineering 131. The students have roughly 6 to 8 hours of homework a week on top of a set number of modules to watch. Then when in class, the students do an in-class activity that is more or less the same as the homework. So again, the type of comment of there's too much work for the class, and if we're going to perfectly follow the flipped classroom model, we're just doing lectures outside of class, no homework. All the homework comes into the class. So again, it's a little bit strange for me to share this with you, the ways that the students think it's not working, but at the same time, I really value that the students are still thinking about the idea and referring back to the sources they looked at the beginning of the year and really, really critically thinking about their classroom experience. So for us, definitely the homework load is a continual challenge that we're working on, where on the one hand, we're trying to make it a manageable load for the students, while at the same time, we know that when they get to their sophomore year, it's going to be even more work for them to do. So we don't want to have them be unprepared for what they'll be seeing in the sophomore year. So it's something we're continuing to try to balance, how to make sure they have enough practice and they're prepared for their future years. Okay, so I mentioned how we've used video modules with more of the MATLAB and Excel and other topics, but then we've also done a little bit with the more real design types of things. For design, we have them work on projects where we follow this sequence, where we give them a problem statement. We ask them to go out and identify their own needs that they want to work on. They need to think about the criteria, constraints, and stakeholders. They need to come up with at least 8 different design ideas. And then after coming up with 8 ideas, think about the pros and cons of those ideas to come up with a short list of 3 to 5, and then go through a process of choosing just one idea, refining it, evaluating it, and communicating it. So last semester, I had them work on this alien-centered design project. So for us, again, with 1,600 students, we haven't been able to scale up so that each of them is working with a real community partner the same way that, that your students do. Definitely, I would prefer that we were able to do that, but for now, we're not there yet. So last semester, to push them to remember that the people that they're designing for are not exactly the same as they are, I had them design for aliens. because aliens are not going to be exactly the same as you are. You can't make the assumption that just because you like something, your user is going to like it if your user is an alien. So that's one example of a design project they worked on. So in this case, we're imagining that alien students are coming to campus next semester. We need to look across campus for things that could be changed or improved to make sure that our exchange students have a positive experience. So they went out and did need finding and took pictures of all kinds of possible issues that aliens could encounter. Related to need finding, we had in the past spent class time watching the IDO Deep Dive video. So this is the Nightline video from several years ago now. I want to say maybe '89, where they went and they filmed IDO designers working on a shopping cart over the course of a week. And so the people from the TV show filmed them for a week, and then they have, I think, a 30-minute version, but there's also a version that's only about 8 minutes long. So you can watch this 8-minute version of the professional designers going out and doing observations and doing interviews of stakeholders to inform their design process. So this is now an opportunity for a video module that students could watch outside of class in preparation for the design topic of need finding. They could watch the IDO YouTube link and then come to class ready to go with need finding. For concept selection, one of the main tools that we work through is this weighted decision matrix, where you need to think about all your criteria for your project, think about how you will measure if the criteria has been met, which of these metrics line up to which criteria, and then rate your different options based on how well they meet the criteria using your metrics. So this is something that we haven't converted to an online module yet, but we plan to do soon to go through this process of using evidence to make decisions about which design option to use. So that one is in progress. And then one that is today, really today. So this morning I taught the first hour of my class, and I had my graduate teaching assistant teach the second hour class. So in the second hour class, they were using Google SketchUp, which I think is now Trimble SketchUp. But again, we had students before class watch some of the video modules, the tutorials that are online to become familiar with this tool. And then in class, they practiced it. So they watched the video ahead of time. In class, they practice it, where there's lots of people that can help them figure out how to use the tool. Where this tool we use to think about how to make their designs more detailed, and also as a way of communicating their final solution. So the next steps for us are creating additional modules, more in the design content, reviewing the homework given the students' concerns, but also just generally looking if there's places where the homework is redundant or unnecessary, if we're already covering it well enough in class. Also looking to see if there's redundancy in the video modules and the mini lectures in class. Because the tension is we want to make sure they really watch the online modules. Sometimes we might err on assuming that they haven't done their homework, so then we start telling them everything in class that they should have seen in the module. But if they did their homework and they watched the module, that can be pretty annoying if we just repeat everything they saw. So we're going to try to work to make sure we're not repeating what was in the video module in the mini lectures. And then considering human voices for the videos instead of the computer ones. And then also back to the issue of the out-of-class quizzes, so we're not burning 10 minutes of class time on that. Those are opportunities for implementation. In terms of research, there's definitely a lot of opportunities we haven't gotten to yet. We've been more in the mode of just being designers and implementing new ideas. But there's opportunities to look at whether students are learning differently or learning more concepts, more content, or just more depth. Are students able to learn on their own more? Are we pushing them to take more responsibility for their learning as we use this method? Are students' experiences with the modules in MATLAB different from the way that they experience modules with design? Do they experience those two different types of topics differently? Or do the video modules work equally well for both MATLAB types of topics and design types? Not sure yet, but another opportunity for research. So generally that has been our design process, where now we're in the space of sharing what we've learned so far with you all to get your feedback, your ideas, your questions. So, questions you have at this point? Yes?
How many credit hours is the class?
Yeah, so another challenge for us. So at Purdue, a lot of classes are three would be like the normal number of credit hours for a class. This class is only 2 credit hours. My personal feeling is that the amount of work we have them do is closer to 3 credit hours. Yep.
How many hours a week does the class actually meet?
The class meets almost 4 hours, so it's 2 class sessions that are an hour and 50 minutes each. Yep.
So if the videos that you're handing out are modular, are the in-class sessions modular too, or?
Yeah, right now they are not, but that is an interesting opportunity to think about. One of the challenges is one of the main things we want students to learn in the class is teaming skills. So then the trick would be to make sure everybody on the team is kind of in the same place so they can still work together as a team. But that's definitely something for us to consider too. Yep.
Online courses, you mentioned the idea of database decision-making or database or evidence-based decision-making, and you've done a lot of surveys and so forth, but when you do online courses, one of the real advantages is that you actually get to see what each individual person, if they're doing these quizzes online, or they're watching the video online, and you're taking data about how much of the video did they watch. I guess there's a certain amount of can they work around it, yes, they can potentially, but I just wonder if that's as far as the data collection about the class, whether that, right now it seems like most of that's being done more hand, right? I mean,
Right.
The surveys that you talked about with the flipped classroom and those kinds of things, those were more on paper, is that right?
So the surveys were online. They were using Qualtrics. Yeah, the surveys were online. The homework is submitted online also so that we can review it online. But yeah, I mean, so 5 years ago, Purdue was using the clickers in the first-year engineering program, and a lot of people have liked the clickers because you can get immediate feedback from the class, how many students understand this concept versus don't. But our experience, at least with 450 students in the class, was you would have students taking up to 10 minutes just to answer the clicker question that should really only take a minute or two, but it ended up taking up a lot more time. And then because we spent so much time waiting to make sure all the students had a chance to respond to the question, we didn't actually have time to process the information live the way that you think that you should be able to with the clickers. So even when you collect information online, sometimes having 120 responses, it still takes a while to go through and get a sense of it. But yeah, it probably would speed things up. Yeah.
Do students have the opportunity to actually write questions based off the videos that they watch that have been discussed in the lecture?
That's a good question. Not yet, but that is something. There is one section that might be doing that, but that is a good idea to try. We've tried to use a discussion board space a little bit too for students to be able to pose questions there. And then there's the opportunity for either other students to respond to the question, but then also members of the instructional team monitor the discussion board. But so far, they haven't really made use of it very much. So that is one thing we've tried that hasn't worked, but submitting questions that could be discussed in class. The trick with that is to figure out what the right cutoff time is. Many of the students like to watch the videos right before class or maybe midnight the night before. So making sure there's time to be able to get the questions from the students in time to discuss them in class. But yeah.
Are the video lectures subtitled?
Yes, you can turn on the closed captioning. Yes. Yeah. Again, we pull some from MathWorks and some from Microsoft, and some of those are not, but the ones we create, we have the captions. So if you are a student and you've watched the module and you're trying to go back and review it, that can be a very fast way to review the module the second time through. Just read the subtitles. Yeah. Other questions?
Thank you.
Thank you.